My name is Reuven Lax. I'm a software engineer on Google Cloud Platform, and we're here with our wonderful partners at Scotiabank to talk about Google Cloud Dataflow streaming and how we autoscale streaming pipelines. And then we will talk about how Scotiabank uses this functionality. So first, a little bit of background on streaming data flow pipelines and streaming pipelines in general, and why autoscaling is important. So unlike traditional batch applications, where you just run once and then they're done, if later you have more data, you run it again with larger set of inputs and more resources. Streaming pipelines are always on. You usually start a streaming cluster, a streaming pipeline, and just leave it running continuously. But in most cases, the incoming load to this streaming pipeline varies over time. Often, these are daily diurnal variations. So, in the 12 o'clock at midnight, you have much lower levels of data coming in. Then at peak hours, your volume increases and keeps going up and down throughout the day. And so traditionally, what people have had to do to deal with this is to provision their streaming pipelines for the peak load. Figure out how many resources do I need to handle the busiest time of day, make sure my streaming pipeline has at least that many resources, sometimes even more, because if anything falls behind, you need to process even faster than that to catch up. And this is very expensive. You're wasting many of the resources throughout most of the day, and one of the things we set out to solve with Dataflow's streaming autoscaling. So here's a quick agenda for this talk. I'm going to start off with a quick overview of Apache Beam and Dataflow and how we execute streaming pipelines. I'm going to talk a bit about what our primary signals are for streaming autoscaling, and how this works today and in our new upcoming streaming engine, which will replace the current one. And then finally, our representative from Scotiabank will talk about how they are using Dataflow and autoscaling to solve their problems. So here we have a visual of essentially the hello world of data processing problems. So the hello world of data processing problem that everybody likes to start with is count words. Read in a bunch of lines and output how many words you have. It's a fairly trivial problem, but it's the getting started guide that everybody uses. So on the right, this is the code you would write with the Apache Beam API, which is the API to Dataflow to count words. This is a streaming pipeline, so we read words from a PubSub topic, split every line into its component words, and here we've decided to window it by 5 minutes. So our output is every 5 minutes, how many of each unique words did we see in that last 5 minutes, and then finally count them and write the data out. Now it turns out that even though this pipeline has 1, 2, 3, 4, 5 steps in it, Dataflow has an optimizer that optimizes this into a smaller number of steps for execution. And what we actually end up with is 2 steps separated by actually the component of this count, where we have to shuffle data around so we can actually count the words properly. And that is the streaming shuffle on the left connecting the 2 steps. And it turns out that when it comes to autoscaling, we can usually look at these 2 steps independently and autoscale each one separately. And also, unlike batch pipelines, where you will have steps in a sequence and usually one step finishes completely, and then when it's done, the next step starts, in a streaming pipeline where data is constantly streaming through, all steps in the pipeline are active at the same time. So you have to your autoscaling algorithms must take into account everything in parallel. So how do I turn on autoscaling? Well, today you turn it on by passing in a flag to your pipeline when you launch it and say autoscaling algorithm equals throughput based. In the future, we plan for autoscaling to just be the default, always on. But until then, this is how you turn it on for streaming pipelines. And you can also specify a max num workers flag, which will give us a ceiling on autoscaling. So if you say max num workers equals 1,000, then we will never autoscale up above 1,000, even if it needs it to keep up with its input. So how does this work under the covers? So to explain a little bit about how our autoscaling works, I have to start off by explaining a little bit about Dataflow's execution model under the covers, how we take a Dataflow program and actually schedule it and run it on GCE workers. And the first thing I have to explain is that in Dataflow, our underlying runner, everything is done in the context of a key. So all data is really separated into key value pairs that we then shuffle around and process. If you've done a group by key or a count by key, or in this case, a count words, then the key is obvious. The key is just the word you're counting. If you were not doing any sort of aggregation, it turns out we still have a key that we just randomly assign to all the elements. We take all the keys. We then we prefix each one with a hash. So we take a hexadecimal hash of each key and put it at the beginning of every key. And which does two things. First of all, it smears out the work. So if you have a lot of keys that are very similar, they don't end up together. It tends to spread them out across the hash space. And also gives us a nice way of chopping this work up. Since every key starts with a 16-character hash, we can then just take ranges of these hashes and use that to divide up the work into multiple shards. So here is an example of stage A. We have taken all the keys. Based off of an estimate of how large we think the input is, we have divided the key ranges up into a certain number of ranges and started the pipeline. So next, we actually start the workers that will run these stages and the streaming pipeline. So here, these little blue icons are our standard GCE icon. We started a number of GCE workers, and for each GCE worker, we take some number of these key ranges and assign it to that worker. So here we have, KRI, KRJ are assigned to this one, KRX, KRY are assigned to that worker. There are more workers in between. Every worker has some number of key ranges for this streaming pipeline assigned. Now, how does this actually work on our system today? And this is This is something that is I'll explain later is changing with the upcoming streaming engine. But the way the current system works is everything runs on these GCE virtual machines. So every virtual machine that has a key range assigned has persistent disks attached to it to store state for that key range. So if you're doing, say, a 5-minute aggregation or a 1-hour windowed aggregation, you need to be able to constantly keep track persistently of what your aggregations are so far for this window. If the worker crashes and has to restart, you don't want to lose any data. So currently, we use persistent disk and a key value store on top of the persistent disk on each VM to store this state. As I'll explain later, we have our new streaming engine moves all of this into the cloud, and so all of this work moves off these workers. You also need to shuffle data. So PubSub is a completely unordered, unsorted source, which means if I'm counting words, all the words might show up on all the workers. So if I want to take the word next, for instance, and count how many nexts I've seen over the past 5 minutes, I need to make sure all these next counts end up on a unique worker so I can do this count. So we have a streaming shuffle system that moves these records around between the workers so we can do these counts. All right, so now that I've talked a little bit about how things work under the covers, let's move on to autoscaling for a second, or for the rest of my talk. In order to scale a pipeline, we need signals. We need something that tells us this pipeline doesn't have enough workers attached to it, we're not keeping up, and also a signal that gives us an estimate of how many workers we need in this pipeline. Your pipeline's not keeping up, you have 15 workers, I estimate that with 25 workers you'll be able to keep up. So what are our primary signals for autoscaling? The first one is backlog. Is there data coming in? If data is coming in faster than we can process it, then the data is going to start piling up and form a backlog. So if this backlog is high, and especially if this backlog keeps growing, that's a sign that we don't have enough workers, and we need to auto-scale up. The second one is throughput. How fast am I currently processing the data? Maybe I'm currently processing the data at 10,000 QPS, 100,000 QPS, or 1,000,000 QPS. But then we have to contrast that with the actual input rate. So the input rate is how fast the data is actually showing up at my pipeline. So if I'm processing data at 1,000,000 QPS and my input rate is 1.2 million QPS, clearly I'm not processing fast enough. And the input rate, we can always estimate the input rate by taking the throughput that we're currently processing data at and then measuring how fast is our backlog growing. So if I'm processing data at, say, 10 gigabytes per second, but then I can measure my backlog and say, okay, but my backlog keeps growing at 1 gigabyte per second, a good estimate of your input rate is 11 gigabytes per second. That's how much, if I was able to process that, my backlog would stop growing. And finally, we look at CPU consumption to understand how much CPU all these workers are using, which is another important signal for autoscaling. So let's talk for a second about backlog. So here we have Cloud PubSub, so a bunch of data coming from Cloud PubSub into our pipeline. Presumably there is a publisher out there that is pushing data into Cloud PubSub. And remember, we had two stages in this pipeline, stage A and stage B. Stage A is the stage that's pulling data from PubSub. So the first thing we want to measure is what is the backlog for stage A? If you're familiar with Google Cloud PubSub will store a backlog for you. In fact, it will store up to 7 days worth of backlog. This can happen if data is getting pushed to PubSub and nobody's pulling from it, or if data is getting pushed to PubSub and you're pulling from PubSub slower than the publishers are publishing. So the first thing we do for stage A is we say, okay, our source is PubSub. Let's ask Google Cloud PubSub what the current backlog is. So we have an internal API that gives us the backlog. It's also available through Stackdriver, so you can go to Stackdriver yourself and look at the unact messages metrics and see what the signal is that we're looking at to know that the backlog is building up in PubSub and faster than we're draining it. But then remember, we have a streaming shuffle between stage A and stage B. Stage B is where we produce the final counts, the final windowed counts for these words. So we need to measure the backlog between stage A and B as well. So if we're pulling data from PubSub and we're keeping up from PubSub, and then we're pushing data to this next stage and say, hey, count words, and the next stage can't keep up, the backlog for that next stage will grow as well. So that also means we don't have enough workers running to maintain our pipeline. So the first backlog tells us we don't have enough workers running to pull from PubSub fast enough. The second backlog tells us we don't have enough workers internally to do all these counts we're trying to do. So in this talk, I'm going to make a few simplifying assumptions to make the auto-scaling algorithm a little bit simpler. So the first assumption is that every stage can be sized independently, that I can go look at every stage of my pipeline, decide what the appropriate number of workers is for that stage, and then I can decide, based off of all of that, how many workers I need for my entire pipeline. Maybe I take the max of all those and say, that's how many workers I need. I'm assuming that that the load is distributed fairly evenly between workers. So if you remember, I said that we put a prefix on all the keys. This actually does a fairly good job of distributing load fairly evenly among all workers. And finally, in practice, we apply smoothing. So as I'll explain in a minute, there's some cost to auto-scaling. So if you have a sudden spike that lasts a second, you don't necessarily want your auto-scaling to go like up, down, up, down, up, down, up, down. So we apply a smoothing window, which currently is in practice, I believe, a 2-minute smoothing window. So we have some sort of, smoother auto-scaling up and down. So what this means that auto-scaling works fairly well when you have continuous variations in load. If your problem is, my load is usually 10 QPS, and then once an hour it spikes to 1 million QPS for 5 seconds, auto-scaling is going to take some time to go up and down for that, for that spike. So, how do we use these signals to actually decide we need to auto-scale up? Well, when the backlog is high, or when we see the backlog is growing, which is a sure sign that we don't have enough resources to run this pipeline, we start generating size recommendations. And we have the Dataflow service in our backend has a loop that is constantly generating size recommendations for a pipeline. So what is a size recommendation? Well, first of all, we measure the input rate. And if you remember, the input rate is the rate we're currently processing at plus the rate at which the backlog for the pipeline is increasing. And that's the estimate of how fast the data is really arriving. After we've measured the input rate, it turns out we're not quite done. It's because if my backlog is currently 1 terabyte and I upscale until I can handle the current input rate of data, my backlog will just stay frozen at 1 terabyte because now I have enough workers to handle the data as it's coming in, but not enough workers to drain that backlog. So we then have to add to that, how many workers do I need to consume that backlog quickly while maintaining the current input rate? Then eventually we will drain that backlog and be at a backlog of 0 or close to 0, and at that point all we need is enough workers to keep up with the input rate. And as I just mentioned, we average this recommendation over a sliding 2-minute window. So we have a little bit of smoothing on these recommendations. So what do we do when the estimated backlog is low? So how do we decide that we have too many workers and we can now downscale this job? Well, I'll divide it into the current world and the new streaming engine world, which is actually in beta and can be tried now. The current world takes a new recommendation, but actually has to be very conservative in downscaling. And the reason why is, if you remember, the current architecture attaches persistent disks to every worker, and the work key ranges are tied to these persistent disks. Empirically, we found that if you get an imbalance, so you start having like 10 persistent disks on this worker and 2 persistent disks on this worker, it actually makes performance worse because the workers with a very small number of persistent disks become a bottleneck for all the other workers. So on the persistent disk architecture, we attempt to only downscale if we can make sure that all the workers have an even number of persistent disks, which often means that if we can downscale by 1 VM, we might hold off and say, that'll create an imbalance. We're going to wait until we can downscale by enough VMs to even out the persistent disks, and only then will we downscale. On streaming engine, our new architecture, there are no persistent disks attached to the VMs. The VMs are stateless, so we can download continuously. So we can just monitor the CPU. We target on downscaling a CPU utilization of 80%. So you do not want to target 100% CPU utilization because that does not give you enough wiggle room. So often you might have small spikes that are not high enough to trigger upscaling, or not long enough to trigger upscaling. You want to actually have enough wiggle room to handle small variations in input. So this is what our worker instance looks like if in the current world. So this is a GC VM. We run the SDK worker. This is the Dataflow or a Beam code that you have written. So this is a Java or a Python process that runs the Dataflow pipeline. There is another process that runs on this VM that is our streaming engine worker. This is the process that knows how to interpret the code you've written and turn it into, persistence, shuffle, and so on. And then there are a number of persistent disks attached to these workers. This is the world we're moving to. So the new world, all of the GC workers are completely stateless. There is no persistent disk attached to them, which means we can just add more or tear them down as we want. There is less cost associated. It's less complex. We don't have to detach disks, move them to another VM, and attach them. And we also do no longer have this restriction of trying to keep an even number of disks attached to each worker because there are no disks to attach. In this world, the Dataflow service and the streaming engine service both run in the cloud, and all the state storage and all the timers and so on also run in the cloud. Which, as a side note, something I forgot to mention earlier, when I was talking about streaming signals, we actually have one more streaming signal. The way windowing works in Dataflow is under the covers, our streaming engine has a notion of timers, where for every key we're processing, it can set timers at the end of the current window, and when the window expires, all these timers fire. And when the timers fire, we say, okay, the window's done for this key, process the count and spit it out. We can measure timer backlog. So we can measure that a lot of timers are about to fire. What this means practically is our autoscaling can see the future in a way. We can detect that, hey, their input rate is still steady, but we're about to hit the end of a window, and all these timers are about to fire. We better start autoscaling now so we don't hit the end of the window and then suddenly start thrashing and wait 2 minutes and then start autoscaling up. So this allows window processing to autoscale much more smoothly by being able to use timers as part of one of our signals. And as I said, no persistent disk, key ranges are fluid. This is in beta, so you can try this today on your pipeline. It is currently only launched in beta right now in 2 regions. So right now, US Central 1 and Europe West 1, I believe, are the 2 regions where we've launched this in. But in one of those 2 regions, you can pass in this experimental flag, and it will run it on the new beta engine. And if you have any issues running this engine, please let us know immediately. This is why things are in beta, so we can shake out all problems with the service before we launch it to GA. So there's some cost to resizing. So in the persistent disk world, the cost is, there's latency detaching and moving disks around or reattaching them. There's some startup latency for a virtual machine. We have to pause work while the rebalance is in process. You add a worker, you have to move some work from another worker to the new one. And for all these reasons, after a resizing event, you need a stabilization window. So what you don't want is a hysteresis problem where I resize and move work around, and that temporarily slows things down slightly, and that makes me think that I'm falling more behind, so I scale up more and scale up more. You can have a positive feedback loop that goes out of control. So after a resizing event, instead, we introduce a stabilization period to make sure the system can quiet down after a resize before we examine it again and decide to resize again. The hope is that our initial estimate on the resize was accurate, so we won't have to resize again quickly. But if we do, we need to wait slightly longer before doing so. And finally, low CPU with high backlog. There are cases in which the backlog keeps going up. We start adding more workers, and then we look at the workers and say, all these workers, none of these VMs are using more than 10% of CPU. All this auto-scaling up is not helping. And the reason why could be that maybe your pipeline is talking to external service and you're being throttled. So adding more workers is not helping matters. It might be making matters worse because you're just hammering that external service even more, and it's going to start throttling you more. Could also be due to a bug in a pipeline. Maybe your pipeline is throwing an exception, and so that's why it's not making progress. We're not helping matters by adding more workers, so more workers can throw exceptions in parallel. So for this reason, we actually have a CPU cap. If the CPU is too low, we stop upscaling. So I mentioned Cloud PubSub. So Cloud PubSub is natively supported. It's by our streaming engine. And there is an API, currently an internal API that we use to measure the backlog and the watermark for Cloud PubSub, although this backlog API is also available via Stackdriver. You can go to Stackdriver and add an oldest unact metric to monitor the backlog for your PubSub topic. The Beam SDK also supports custom sources. So if you have a custom source, you have to implement these two methods which allow you to report what the current backlog of your custom source is, and we can use that to estimate backlog on the source and upscale. If you have a source that doesn't report those, upscaling will still happen based off our internal backlog measurement, but it will not work as well because we cannot measure what the actual backlog on the source is. And PubSub.io, which I already mentioned, our Kafka source and our Kinesis source support this out of the box. So if you use either Kafka or Kinesis, backlog will be measured. So in conclusion, I talked about our primary signals for autoscaling, a bit about how our Java SDK is supported for autoscaling. Python streaming, which is currently in beta, will be supporting autoscaling very, very soon. And the new streaming engine, which is currently in beta, will take our existing autoscaling and make it work that much better. And now I'm delighted to introduce Roy Bryant from Scotiabank. Scotiabank has been one of the leaders in the financial services industry of moving their processing over to Google Cloud Platform, especially this type of data processing. And Roy is here to tell us a little bit about what they've done and how they've done it.
Thanks, Reuven. So I'm going to bring it up a little bit higher level. Reuven's been talking about the details of how Dataflow works, and I'm just going to talk a bit about the use cases we're using. We're trying to transform the bank. PubSub and Dataflow are foundational to that, so I just want to talk a bit about what we're doing. A little bit about Scotiabank, in case you don't know anything about it. The bank's been around a long time. It's in the top 40 or 25 largest banks in the world, depending on how you measure that. It's really international. It was founded in Nova Scotia long ago and doing trade that came into the port. So more than half the business is outside Canada. There's business in 55 countries. 23 million customers, which is getting close to the population of Canada. And so we've got a few challenges in the infrastructure. Part of it is it's been around a long time, so we have legacy back-end systems, more than 50 years old. We're doing lots of digital banking and transformation online stuff in many regions, many countries, so we want to go fast there. We've also done a lot of acquisitions, so over one 10-year period, we acquired 30 banks, each with 2 data centers. We have lots of data centers in sort of this effort to consolidate that and rationalize the stacks. So we've got some complexity. So the trust and the reputation is foundational to the business, as it is with the financial services, across financial services. And how we handle PII is key to that. So big step is moving the PII to the cloud and making sure that's entirely safe. And we've got a lot of stakeholders, security and operations, as every large organization does. We also have, in addition to legal, we've got internal and external auditing, we've got regulators, and we're in 55 countries, so we've got 55 regulators. And and then there's a tension about the velocity. For the digital, we want to go fast and iterate and get features out to customers, moving agile. And then we also have a lot of back-end infrastructure teams that we care a lot about stability and reliability and everything. We actually want both places. We want the digital stuff to be stable and reliable, and we want to bring more velocity to the core banking systems. So we're trying to do that using cloud. When we think about cloud, we're thinking about it more as a method rather than a destination. So we conflate cloud as moving it to cloud, along with DevOps and CI/CD and test-driven development and all those pieces. So we've got 2 production systems that are using PubSub and Dataflow. First one I'll talk about is our log streaming. So we've got pulling in structured and unstructured data and logs from Stackdriver from many different sources from all the projects running. And then we publish those to PubSub and then use Dataflow to route those to secure SecOps and persist them for regulatory purposes, feed it back to ops, all that kind of thing. And for this, we found it works. PubSub and Dataflow work well, and they're performant, and they give us the performance we need, and we don't really see any issue with that going forward. So we're happy with it. This isn't really transformational. I think the second use case is more interesting because it's the foundation for how we're transforming the bank. So for this, the problem we're trying to solve is we've got a lot of different back-end systems with many data sources. So in Canadian banking, we've got over 2,000 production databases, all with data in different formats and different representations. No agreement on what a customer is and what a first name of a customer is and what an account is and so forth. So we're trying to rationalize that. And then, so it's a 2,000 in Canada, and we're in 55 countries. We're not going to, in place, to start refactoring all our databases. It's just not going to work. So what we're doing is we're using cloud as an opportunity to restructure the way we do all this. So on ingestion, we're transforming the data into a standard format. So we've got an enterprise data model and a business glossary that you can define what exactly is a customer, what is the customer's first name, and then we map from local schemas in all the different data sources. We bring that in, we map it to the standard schema, see in the, say this is the customer's first name, this is an account number. All that, bring the data all into one place. That does a bunch of things. One is that we can now, it opens the door for doing analytics, and you can do analytics across, many data sources, all the performance and so forth from that. The other thing is that it puts a cache of the data in cloud. So we've got banks, we do a bunch of Canadian banking, and we've got, you're using your handset and you're doing online banking. And then we've got backends in Toronto, we've got backends in Chile, everything's far apart. So what we're doing is we're taking a cache of things in cloud, so you can we can put the compute close to the data. So so we're using this, we're calling this the event layer. This event layer, there's the 2 pieces that PubSub and Dataflow are key in. One is the ingesting the data into the common format. So for here, we're streaming from back-end systems, and it's MQ, COBOL copybook, whatever, down there, transform that, stream that up into cloud, it comes into PubSub, and then we use Dataflow. So on ingestion, we're transforming it to the standard schema. We're also using DLP and KMS and tokenizing the data. So we've got it in flight, comes in, and then in Dataflow, call DLP on the fly as it flows through, tokenize that, land it in Spanner. Now it's all encrypted, safe there, and then we lock down re-identification separately. So so there's the standard format, getting the cache. The other piece is moving to event-driven. So we're taking events that can be infrastructure events or security or operations. Also just changes in back-end data. We're detecting that, raising an event for that, or a transaction comes in, and then we're persisting the transactions. So now instead of the application needing to figure out how to talk to, many back-end systems and having the business logic in the application and in the back-end systems and the APIs, and APIs call other APIs, and it's really hard to tell what the business logic is. So instead of that, changing it to the event flow, and then that gives us all the data in the cloud. And then when we start looking forward, we can see what are the changes in the back-end system. So if we can understand the data and we build up a history of exactly how the data changes on events, we can start, reversing out and making sure that we've got the business logic right. So if we're trying to replace a back-end system, we can run it again. We've got some code that we assert works the same way. You can run it through all the, the last year's transactions and see if you get the same answer every time. So, and then for the APIs, so we're trying to break out, we don't want all these layered APIs on the back-end systems. So what we do is we bring the data into the event layer. Then you can applications can either subscribe to the stream of events and see transactions that way, or can query the storage, or we also expose it through APIs. So we have a data as a service API that lets you access API-driven, do the queries against the data. And then we have a bank as an API level above that with bank concepts. So you can say, what are the accounts that this customer has? And then it'll use the data APIs, it can do the queries, give a structured way to get at that. So what we've accomplished, so we have these couple of things in production. And we've used, and as I said, the transformation to standardized data and event-driven is really foundational to our strategy for transforming the bank. And then PubSub and Dataflow are foundational to the implementation of that strategy. And we've been really happy with the performance, the cost, reliability of the systems. They've all worked really well in production. The other factor we considered in choosing Google to do this is there's a really strong relationship, a collaborative relationship, and we get a lot of engineering support. So this has gone really well. Thank you.